Welcome to boiling point elevation and freezing point depression. So, boiling point elevation, freezing point depression, and osmotic pressure are called colligative properties. Because they depend only upon the number of particles present in solution, they don't depend upon the identity of the particles. So, recall that the boiling point of a substance is the temperature at which the vapor pressure equals the atmospheric pressure. So if the vapor pressure of a solution is lower than the vapor pressure of the pure solvent, then the temperature at which the vapor pressure of the solution is equal to the atmospheric pressure must be higher than the temperature for the pure solvent. So when we dissolve some solute into our solvent, the vapor pressure of our solvent drops. That means that if we were at the boiling point, our solvent vapor pressure is equal to the atmospheric pressure. Let's say it's 1 atmosphere, 760 torr. When we put our solute in, now that vapor pressure drops, that means that our solvent will no longer be boiling. It was boiling before because the vapor pressure was equal to the pressure, the atmospheric pressure above it, but now it's lower. So now, in order to get that vapor pressure back up to atmospheric pressure again, we have to heat to a higher temperature. Okay? So this is why the temperature, the boiling point, goes up when we dissolve some solute into our solvent. So know that the vaporization curve for our solution is lower than the vapor pressure for our solvent. So the vapor pressure of pure water is in red here. The vapor pressure of some solution is in blue. So we've moved the whole curve down and to the left. So this means that because the vapor pressure is lower, in order to get some pressure, at any pressure in here, in order to get to that point as a pure water, so if this red line is at 1 atmosphere, then this intersection point there is 100 degrees Celsius, the boiling point of water, normal boiling point of water. If we dissolve our solute in, now that temperature has moved to the right for that same pressure. Temperature moving to the right means a higher temperature. We have to go to a higher temperature. So, to obtain the same vapor pressure, the solution must be at a higher temperature than the pure solvent, and that means the boiling point of our solution is higher than the boiling point of our pure solvent was. So, this change in boiling point can be calculated by this equation. So we have delta T is equal to Kb m solute, where delta T is our boiling point elevation. Kb is called the molal boiling point elevation constant and is characteristic of our solvent. So if it's water, then Kb depends on water. If it's something other than water, it depends on the identity of your solvent. And this M solute is the molality of the solute in solution. It's not the mass of solute, it's the molality of our solute in solution. So note that the melting curve for the solution is farther to the left than that for the pure solvent, so this is the same graph as before. And now the melting curve is this almost vertical line. In this case, it is shifted to the left, so this is as it would be for water. So at some pressure, where that pressure line intersects with the melting curve is the normal melting point. So for the pure solvent, it's here. For the solution, it's farther to the left. So for the solution, the temperature farther to the left means a lower temperature. So the freezing point or the melting point for the solution is lower than the melting point for the pure solvent is. And this means that our solute is causing a decrease, a depression of our freezing point. Remember, it was an elevation. We were moving it to the right, a higher temperature for the boiling point, but the freezing point moves to the left, a lower temperature. So we're lowering the freezing point, we're lowering the melting point when we add a solute, and we're also raising the boiling point. So this change in boiling, in freezing point, this change in freezing point can be calculated by a similar equation to the boiling point expression. So delta T is equal to Kf m solute, where now delta T is still the not boiling point, freezing point depression, and Kf is the mole freezing point depression constant and is characteristic of the solvent, just like Kb was for the boiling point elevation, and M solute is still the molality of our solute in solution. Note that Kf and Kb are not the same value for a solvent. So that was boiling point elevation and freezing point depression.